we continue? So me is missing, and who is missing? Alf is also missing. No, I'm yes. All right, so I'm going to start with your question, and then we will do this. Usual questions. Well, you told me that you know what our VA are. Record. Record. So let's say you have some variable. So let's say you have y. Y equals maybe mu. So cos say a1 t minus 1 plus ut. So that's a vector u. Order of the VAR. Dimension k. The k variables here. But that's actually one variable. So for example, it could be GDP growth of Vietnam. That's the supply. So it's not, and we have the supply shocks. Then we look at the inflation. Well, that is so GDP growth and inflation. So two variables. You can basically go and then feed the VAR. You can have more variables, but then it's a stable two. But then so let's say hard field now, then we want to look at China too, and Taiwan, and Thailand, and Japan, and Russia, and so on and so forth. So not only an equation for one country, for many countries. Say, then there is an R. Yeah. So that becomes a Hammond vector autoregression. Okay. So, well, it could be a global VAR. So many countries. We look at all of the OECD countries, all of the Africans, and so on and so forth. Right. So I have a global VAR paper for sub-Saharan Africa. It's an old paper, but it's an IMF paper. Maybe after this sort of session, maybe you can take a look at it. Just for Google it. So VAR, global VAR, and so on and so forth for sub-Saharan and there are many papers. Just remember my work. But now the thing is that something may go on here, right? Then because that's becoming many countries, right? Then there may be somehow some variables which will not include in here. So you have some sort of problem with your estimation. Okay. For example, let's say this UIT may be essentially affected by a factor which is a global factor. For example, let's say oil price shocks. Right? So there are something that affects all of the countries. Right? So it's not specific to one country, but it is somehow affecting all of them. Right? Or let's say the volatility index, VIX. Right? So that's also one index. Or say tandem index. There is a tandem index and can look at it. So it becomes high or low depending on whether you are independent or not. became more important when this COVID broke, but this has existed for long. And so to speak, there are many variables which are common to all of these countries. But they affect them differently. So clear. So what I mean, essentially this could be a function of some factors, let's call it FT. So it could be R, so or it shows at the loop, and so on and so forth. But they are in here. And well, they affect each country differently. The coefficients is different. And so to speak, this U can have one component like that, and then plus some idiosyncratic variable. So I mean, apart from these factors, well, not all of the variabilities in U is explained by this decomposition, right? But there is always something left, right? Which is the underlying what idiosyncratic variable as a code. Right? So these are basically some variables you don't, I mean, you may know them. Right? So variables like this I mentioned, or oil price shocks, right? Or whatever else you may think of that affects the globe, affects everyone. And then, so they are common across all of them. So these are called common factors. Common factors that we have, so they are essentially the same across, so they are the same variables for all of the countries, but they affect them differently. And this is called a factor, and this is called the loading. So there is a load. So these are factor loadings. And why do we call them loadings? Because they load the factors onto our equation, like coefficients essentially. That's a multiplicative component. I index is here for the coefficient essentially, right? Well, these coefficients are homogeneous, they're the same for all of the countries, this is the same for all of the countries, but this varies from one country to the other. This is a factor which is common across all. Now the thing is that sometimes you know these common factors because of your knowledge of the macroeconomy or the financial system and so on and so forth. Sometimes you don't know. If you know them, for God's sake, go and use them. Put them in here and do the estimation. And then you will get an A which is also we can measure on the factors. If you don't know them, then you have to use principal component. So that's sort of one application of this. Then this actually model with the factors is not a way, it's still a VAR, but it is a factor augmented VAR. Or fallback quotient. So this is one application of the factor models. And how do we get the factors that we now talk about? We of course did it as PCA. Alright. But then we have to decide on how many factors. Right? So that would be your second question, the second question that you raised. So that's sort of one interesting application that came. There are very many interesting papers on fallbacks, which help you essentially understand, okay, well, once you bring them in, then sort of the impulse response that you get here become more precise. Because you're sort of conditional more explanatory variables. So there is also another thing. Let's say I'm not interested in these factors, alright? But I mean, let's see. I mean, this UIT, so that was a macroeconomic application, right? Could be also finance, of course, right? You have many assets, and then you estimate them together, and then there is one factor that affects all of the assets, some global factor that may be there. But then there is also something else. Let's look at UIT, alright? UIT has this factor in common. Right? So say China has this factor with a different load. Taiwan has this factor with the same different load. Vietnam too. Right? So loading just changes. So there is one variable or one component here which is common across all of the shocks. this makes UIT to be dependent across countries. So to speak, oftentimes when you come to factor models, you want to appreciate the fact that there is cross-sectional dependencies. So across the cross-sectional, so section 1 is country 1, section 2 is country 2, and so on and so forth. And they may be dependent to each other. And because what was factor models intrinsically, when they came also sort of to econometrics, one of the reasons that they became very popular were that you could use them to model cross-sectional dependence. So that's sort of another usage of those. Because well, if you have cross-sectional dependence and you take care of them, right, then the residuals will be having less variability because you can measure on that. So, well, this is like a big variance, has a big variance. Once you take part of it, then a smaller part will be left. So the variance of the shocks will be less, and the estimates will be more precise. So it's also interesting. So it's sort of killing two birds with one stone. You have the cross-sectional dependence, and then you reduce the variability in your estimates, which is nice. All right. And so that's sort of one interesting application of these factors. Now the question will become, how do we estimate them? All right. So if I know them, I use them. If I don't know them, or I don't know how to basically forget them somehow. I don't know F, I don't know lambda. None of them I know. All right. So that brings me to the estimation also his question. But let's say you have, instead of UIT, let me use XIT. So XIT is some variables. So they could be all of the variables that you have on a macro economy. All of the variables that you have on a financial system. There are many things that you observe them. So each I is for one variable, and T is the time that you sort of observe it across time. Now we want to estimate the factor that we have here, that we have common to all of these x's. Then what we want to do. Then we say, all right, so let's say we have lambda I times f t and plus some error u I t. Right? That's what we could do. All right, so we start with saying, okay, so if I have a factor structure, then we can start. Well, my notation is a little bit different. So here I have xti doesn't have. So let's basically stay with the notation that I have here. So that will be better. So I have all of these factors. Let's say they are R factors. Lambdas are the loadings, and then we decompose this like that. I don't know F. I don't know lambda. So, but how do we actually estimate them? Right? So that's sort of a question that sort of is interesting. Right? Now, before we go on, it is important for you to know that these factors you cannot estimate uniquely. Right? You don't know F, you don't know lambda. Right? Now, let's say I tell you x times 1 is 1. Right? Then what? And then this actually probability. Well, let's say you tell me that the solution is 2 and 1/2. Right? So 2 times 1/2 is 1, right? But I can actually say this is not the only solution, there are more than 1. So I can say, all right, so let me multiply this 2 with some R, right? And then this 1/2 with inverse. And then you choose R to 10 to 5 to whatever. And you still will have, you can, by varying R, as long as R is not 0, then I can actually generate all of the solutions to this. Right? Well, and here, because these are matrices, so these F and lambda are matrices, then you can choose some matrix which is like so. So I have R facing vertical. Like here I've chosen one-dimensional. Invertible means that it's non-zero. Then R minus 1R is can rotate factors like so. Now that's like a rotation. And so when you pre-multiply a matrix by another one, then you sort of rotate them. This is what you do more or less. Maybe I should tell you a bit about the rotation. But later. Well, let's focus on that. It will be an interesting digression. So it means that factors you cannot estimate uniquely. They are, you can estimate them up to a rotation. Right? So they're infinitely many. So that's sort of, an issue with respect to this. All right? And probably you know with the VAR models that so when you estimate the impulse responses, then you need a decomposition of the variance covariance. So you get the fundamental shock, and it's not unique. You generally use Coalescent, which requires that you order the shocks in VAR. Right? Well, that's a problem which persists and is here too. So we can just estimate these up to a rotation, as I just said. Right? So let's forget about this rotation for the moment. So just not focus on that because there is no solution to it. All right. And then let's go on and then see what can we do. Let's augment all of these, or stack all of these observations together. So across I, and then the error terms across I, lambdas across O. Right? So we have an equation which is stacked. Right? For all of the countries, for all of the units that we have across time. So that would be our the variables that we have stacked across countries, units, and so on and so forth. But you can do one more layer of augmentation. Alright. Then you sort of, those variables that we have across time, then you also augment them again. Alright. Such that we have a very big model. Alright. So these are all of the F's augmented or stacked for all of the countries, for all of the time periods. Alright. Times lambda is plus E. So error term, that is EX. Alright. Now I want to find F and lambda. Alright. Well, if I had a regression, if I had say Y equals X beta plus U, then you know how to estimate beta. So beta hat is X prime X minus 1 X prime Y. Well, you know X, you know Y, you know an estimate for beta hat. Right? But here I don't have F, like my x's in that equation, and lambda like the coefficients. I don't have any of them. Right? So that I can't do the estimation like that. Right? So but let's assume, let's make an assumption that we know F. Let's say I know. That's not realistic, but you can always make assumptions. I can assume that this room is blue. And I can assume that F is known. So let's say we have some estimation of F. I call it F theta. If I know it, F, then I can get the coefficients. I can plug in this equation and get the coefficients. That's not what we have. Right? So I can say, all right, if I know F, then lambda will be known. So if I know that those guys, if I can get lambda as a function, well, these are tildes, so they are not known yet. Right? But that actually says that lambda and F should be related like this. Right? So then, then I can get the residual of the regression. Right? The residual will be the left-hand side variable, which is X. The variables which I don't know times the estimates of the lambdas. So that will be E. And then if I plug in here, then this is the annihilator matrix. So that's I minus that. That's the M matrix. Right? Then I have the residuals. Right? But if I have the residuals, then I can calculate the sum of the squared of the residuals. Alright, so which is summation of all of those. I can write it like this. Alright, well, that's the sum of the square. That's E prime. These are vectors. E prime E, which is essentially the trace. That's the summation of all of the diagonal. Okay? So these are all clear. So then I can go and minimize this. Sum of the square of the errors. And then sort of find, well, my f's and lambdas maybe at the same time. So if you look at E is a function of f. Right? Previously, so whenever you were doing this, because x is known, then sum of the square of the residuals is a function of beta. Alright. And you minimize that in beta. So here I have the sum of the square of the residuals. They are a function of f, which I didn't know. So I can go minimize that in f. Alright. That's how you can actually approach estimation of the factors. Clear? Well, but then with factors you need to be orthogonal to each other. Remember from principal component that we had say A1 times A1 prime times A1 was 1, right? That's what we had. But we needed also. And say A2 prime times A1 was 0. So that we have essentially the orthogonal to each other. And that is what we can do here. So I can say that the factors times themselves were divided by t, because these are observations. Right? So there will be some normalization factor that you need here, because here you sum them. So all of the factors and you divide by t, so that we have an expected value, so to speak. So the expected value t is large, the expected value of those are in such a way that they are, that's an identity matrix of dimension R. Right? So that's the diagonal elements are 1, off diagonals are 0. They will become orthogonal. And so to speak, we minimize that guy subject to this constraint, that f prime f is indeed identity times this t, which is the scale essentially. Alright? So now, so if you want to minimize that function, so well, this discussion actually links what we did with the principal components with all these factor ones. So here, so E tilde is like x minus f tilde or t minus 1 f tilde prime times x. Right? So that is what we have. So in this, well, there was an x prime x minus 1 or f prime f minus 1 in here. But because f prime f is this identity matrix, it becomes identity times t squared, t to the power of minus 1. So it becomes like that. And then, so we want to minimize this. We want to minimize the trace of E tilde prime E tilde in F. Alright, so then we play around with that. Let's call it T bar. So that's the trace. That's sum of the square of the residuals, right? Do you agree? Right. Well, now we can go on and we calculate the E prime E. E tilde prime E tilde, that is, well, x minus f tilde t minus 1 f tilde prime x is zero. So x minus f tilde t minus 1 f tilde prime x. Right? So now we multiply. So I need a trace of that. And that is a trace of this. Well, that would be the trace of with x prime x. So the trace is linear. The trace of a plus b is trace of a plus trace of b. That's what we're going to do. So x prime x minus trace of, well, here then that's a prime. So that becomes x prime. That's this. So then I have say f tilde t minus 1 f tilde prime, that's the other term. Now I have x prime times that. So that is minus trace of x prime f tilde t minus 1 f tilde prime x. And now plus the last trace. want to sort of play a little bit around with that, right? Look, so f prime times f, f prime times f is t on, and then so one of the t's with one of the t's cancels, right? Then, so well, let's say this whole thing is identity of dimension r. And then here you have x prime f t minus 1 f prime x. That's a plus. And then we have a minus, so then they cancel. So, did I say it correctly? You're right. Okay. Exactly. So let's sort of say, let's simplify it. You are this one. So x prime x, so that's the first, x prime f prime, well, there is an x here. So here we have x prime x, and x prime, I forgot the x. Alright. Right, we let x and 4. So one of these cancel, and then we get this is to be equal to the trace of x prime x minus trace of x prime f t minus 1 f prime x. Right, so that's sort of what we have essentially here. Right. Okay. So now can you see why this last term can be written like that? Well, I mean, you see, so here we have x prime x outside, and then f prime. F prime is not identity, right? We won't do that. It's because f prime f is the ortho vector. So that's different. So if I had here f prime f, then it would have been 0, right? But this is not. So if I had f prime f, then it would have been identity, and the whole thing would have been 0. Right? Let me maybe remind you of something. So let's say we have trace of A, B, C. We can change the order. Right? So the trace doesn't change. And then exactly. You remember that. Very nice. So here we have the same thing. Right? And we can change the orders. Right? As long as they are conformable, then the trace value will remain. That's a property of the trace. Right? So this is the trace of x prime. These are the observations that we have. This is f prime, unknown. Right? x prime. So I want to have this divided by t. Why? Because if t becomes very large, then this becomes the covariance matrix. Right? So if I want to minimize that, well, this is not a function of f. There is no f here. So I have to maximize this. Right? So I have to maximize the second trace. So minimizing, so here min in f tilde of trace of e tilde prime theta is equivalent to maximizing this trace. Change the order. So here we have, comes first f prime theta, and then we have x prime divided by t tilde. But this is minimizes and we can ask. Well, now you should see the point of everything that we did in the previous section, and then the matrix format, right? Remember we had, say, we were maximizing a prime sigma a, subject to a prime a is 1. Remember? So that's some matrix factors. Or so to speak, how do we get the common factors? Right? Okay. So, now because this is a regression, so then we started with R factors, then we have to find the R, then sort of the question is such that we have parsimony, not too many factors, but we need to get a good minimum for the sum of the square of the residuals. And then we need an information criteria. And the information criteria looks like these are all of the stuff that we did, some other asymptotic stuff. That is the so that's the well. I mean, let's say you estimated with one factor. You assume R is 1, and 2, and 3, and so on and so forth. For each of them, then you have a normalized sum of the square of the residuals. So that's the variance. You can think of it as the variance. Well, that's the variance. Remember? Then, well, the information criteria then always have the log of the variance plus some punishment. Right? And then here you have the punishment term. So N is the number of the countries, T is the sample size in time, right? And K is the number of the factors. So you choose K such that this is minimized. Right? So that's the way that you choose the number of factors. So that's we need an information criteria, and that is the one. Well, this information criteria comes from a very famous paper in econometrics from 2003 by Luke and Bai. What's the name? Selena. She's Korean. And then Bai. I don't remember. But they are very famous people. So they have a paper in 2003 where they say, okay, this is the way when you sort of interested in the number of factors like that, right? Then asymptotically, when the number of the countries become large, right? The number of time series also become large, so 2 dimensions become big. Then this K, which minimizes this, will recover the true number of factors. Right? That's an old paper. And there has been a lot of refinements and it made it better, and so on and so forth. Okay. That's okay. It's not the best basically criteria. There are better ones. Sorry. But then, well, this is a good thing to start with, and that's manageable. One can program it using Python to find the number of factors. That's how we choose it. That's by name, and then we added in 2002 to make sure that this is asymptotically equal to the true factors. There are some other tests. That's Alexei Onatsky's paper. They are very hard papers to read. But then there are other tests, as I just mentioned. And then we know how to choose sort of, you know a bit of theory of this decomposition of the factors, right? The theory, you know where they come from. It's a very simple sum of the square of the residuals. The solution is in terms of a vector, and then the solution comes from this theory also given. So you know how vector models are made in basic form. And that's a usage software. Okay. And I also told you how to get the PCAs using Python. Comes from the scalar. And that brings me to an end of this slide. You mean,
That's why you have the noun over here.
yes, I don't think the mean is zero. Maybe I will.
Because I remember the formula is like this, even it goes to 100.
So everyone you should take this and then take the mean off. Just add them. So here 32.
48, yeah.
46, 56, 58, so it's 58 positive. You should demean them too. So that should be x prime minus x bar times x minus x bar. Very nice question.
And
Over n is this n minus 1. So, but then I didn't care about that. Very nice. Okay. Well, let me look at some of the assignments very briefly. I don't have so much time to do them all, but I can give you some brief review of them. All right, so some of them. Well, I added something on Markov processes, Markov chains. That's the last question. So let's open it. I just want. That's actually an interesting question.
Just question 9.
I also have a question.
Yeah, you can ask. I will just briefly maybe talk about this and then we go on.
Yeah.
So that's a simple Markov chain. I'll tell you what it is about, and then we go on. I mean, companies have credit ratings, you know, right?
yeah.
So that's sort of that they are good, they are strong, B, blah, blah, blah. Right? So, and then there are AAA, AA, A, triple B, double B, and so on and so forth. I didn't include them all because they were, the matrix would have been very large. Okay? So here I stated with 5. Alright. Well, I mean, let's say that companies actually, well, I mean, they're sometime for a long period of time, let's say you have a triple A, but after some time it may change, become a double A. Right? So maybe you have a double B or a B, and then you default after some time, right? So, well, I mean, you can think of this as some transition from one status you go to some other. In Markov basically change. So you want to understand, say, how companies actually move from one credit rating to the other one. And one way of understanding this transition is by turning back to a Markov chain process. Right? And then, well, here I put together the transition matrix. Well, well, I mean, let's say this is point 1. So this is the fraction of time that somebody is in triple A now, and then goes to a double A. You can look at all of the history of all of the companies, and then see what was the fraction. If you were a triple A, and the next year you went to a double A. And then I made it to be 10%. Made them up. Alright. But these probabilities, of course, you can estimate, alright, as a function of macroeconomic parameters, so sort of company-specific information. Somehow one can go and estimate them. Once you have them, then you will be able to understand how the transition is, correct? So from, say, one status to the other. So if I start at, so if you are in a default, the next period that you are still in default, because you are dead. Well, that's a status which we call it that's like a hole. It's a bed. You fall in it and then you don't come out. That's an absorbing state. And then the diagonal elements are interesting here. Right? So with probability 1, you stay in default when you are in default. Right? So 85 is with probability of 85%, then I will be triple A if I am this period in triple A. Right? And so on and so forth. So that's sort of the dynamics of things. But that's an interesting indeed application of the Markov chains. Well, some finance related, of course, people want to give you. That's sort of a very simple one. And of course, as I said, so these probabilities should be estimated, they may be time varying. right? So depending on some other like variables, and then you are asking very simple questions, which delete. So if I am in a technical A, if I'm a double A, so what is the probability the next period I default, right? And so on and so forth. So they are they're not complicated, but once you know how the Markov chains work, then you can do it. That was one of the assignments which I wanted to talk about. One other one I want to talk about is this here, and then you ask your questions. So that is something we did. Alright, so that is with respect to the value at risk. Alright. So value at risk is an important indeed indicator. People use it for risk management. Indeed, in Basel 2.3, and this is actually binding, to calculate the value at risk at 1 day horizon. Right? 1 day value at risk at the level of 99%. Right? And then here, well, I mean, long time ago, before the financial crisis 2007-8, most of the companies that were calculating the value at risk using historical data. So they were looking at the last 5 years of data, calculating a variance, multiplying by a critical value, right, of Z of say 0.1, and then going on. So that was what they were doing. And that was wrong. They were not really reflecting the true variance and that they have had, the risk was. So the value at risk that they had was in 2002. So then Basel had revisions, and then they were required to do it differently. All right. So now that it's more relevant, the estimation of the risk, the utility is done better. And this exercise actually less than 99%, so you have base data. I wanted them to estimate the volatility using a gauge 1-1 and also an asymmetric gauge, a GJR. Alright, so where you have this gamma showing up with the shocks being negative and positive. Alright. And I wanted that you go and then calculate how many times the returns tomorrow are actually below the 99% quantile, 1% quantile. Right. Right. Let's say we have a sample of, say 2,000, so 1 till 2,000. Right. Say that we have like that. I think I said it to 500. Let's say we stay at day 99,099, T minus 4. And then we go 250. So we basically go to here. So 1,999 minus 250. So this defines a window. Okay. And then here we estimate a large 1-1. Okay. And then we estimate a GJR, also 1. So also large 1. So we estimate using these observations the last 250. And provide a forecast for volatility for day 2000. What do you have? Okay, so you get a forecast here. That will be sigma I. For these 2 months, for day 2000, given the information that we have in this window, till minus till this window. So T, whatever, this one minus E. Right? Then you will have a value, right?
Yeah.
And then based on this value, you can calculate the value at risk for tomorrow. You predict it. Now you go to day 2000, and then you have the return, right? Because it's observed. And then you see, is it below this value at risk that you calculate this or not? If it is below, then values that we calculate here, or you are not. Okay, so now we have one value. And then let's say we change it, we sort of move this. Alright, so leave it. Okay. So now we do it not at 2099, but rather we do it at 98. And then we go to 98. And then we basically do this again. Now, do I have a breach? Yes or no? Using both models. Okay. And then you go to the beginning. In 1 till 250. Alright. So for 250, then you do the estimation, go to day 51, 251, estimate the volatility or forecast it for this and that, and then see whether you have a breach. So if you do this, then how many breaches will you calculate? Well, you will calculate 2000 minus 250. Right? 2000 minus 250 will be all of the breaches that we have. So there will be zeros or ones. So, and well, you sort of you require that all of these breaches, well, are 90, well, I mean not 1 minus 99%. So 1 minus 0.99, which is 1%. You need to have only 1% of the breaches. So if they are, well, 2000 minus that, it's 1750 times 1%, then is, well, 17.5. So that's the bracket, the number. But we require not to have more than this number of breaches for all of these time periods. Yeah. But here you have two models, the gauge and the asymmetric gauge. So now the thing is that so these models should be as close as to 17.5. Right? So if one actually estimates less, then it doesn't understand the risk. So if you sort of underestimate, then it's bad because you have the risk that you didn't understand. If it estimates more, then it gives you wrong signals. Right? So sort of you're okay, but this actually says that you're not. Right? So now one of these models will actually do better in getting the true breaches. But there will be some number, right? So some number we should be around this. Some may be more, some may be less. So if you have too many more, then you will be punished. Right? You're not doing good. You're taking more risk as you are allowed to. Right? And well, to really understand whether you have a problem or not, then you should be able to calculate the value of this problem. Right? And the question is that which of these is better in getting the number of breaches? And you will find that this is better. GAJR should be better. So we give you a number which is closer to 70, 80 compared to the large. It's also one other usage of these asymmetries. So asymmetries are better in getting the, when you include them, they are better in getting the value of risk, providing you with better estimates. For the fun of it, then you can also look at, say, a rolling window. Or maybe using all of the observations, sort of, just to see what happens. That was the point of this exercise. So you see some usage of these models with respect to regulations. Well, that's Basel III here, that's important. Okay. These were the two ones that I wanted to talk about. And now you should become quiet and you ask. If you have a question. Lee, you said you have.
Later the mark G.
Right. Okay.
Physics trueness is one of December.
This was the exam of December.
Yeah.
Exam question of not December but March this year. Example or December? Sorry, I didn't understand.
December.
Example
Exam.
of what?
Of the question I asked.
You question. Yes. Yeah. Okay. Alright,
Because
Brian.
the credits, active credit may not affected by the economy
Sure.
environment.
Right. Right.
Yeah.
But when you are asking me something about your own question, right? That you have, say, two estates,
Yeah.
but it may not be actually enough, right? Sorry, I'm not really sure if I understand the question.
I mean, the
Yes, please come in.
so we have
Alo, alo,
it's all like the same.
Ah, yes. Regions. Or blue ones. So regime 0 or 1. High or low? That's correct. Okay. Now it is. But I mean, I actually, so that was the day that you were not here, and I made up an example out of your question. Right? And maybe I just review it. Okay? And now I understand. So look, I mean, let's say, so I'm going to simplify it. Let's say we have some data which look like that. Right? They're normally distributed. Right? And they are in such a way that here we have a high mean, mean is 3, and variance is low. Right? So variance is 0.5. Right? Then the mean drops and the variance is large. Then the mean grows and variance is large. Alright? And then the mean is dropping, variance also dropping. So we have 4 states. Like not 0 and 1, not high and low, but rather high, low, low, high, low, low, high, high. Right? Okay, so we have 4. It's what I mean, not this regression, but that's sort of a little bit simpler in the sense that we have just a mean and a variance. Right? So that we have 4. And there we can do 2. And then the question is then how does Markov switching model actually deal with this? Alright. So let's actually go on and estimate this using 2, 3, or 4. Alright. So sort of Markov models and then look at it. Alright. So this is the loop that we have. And well, use goes and estimates them. And I will now talk about this loop. Well, let's let it finish, and I will start talking about, say, the quantities. For example, let's say we assume 2 factors. That one is when one is high, then the other is high. When one is low, then the other is also low. Alright? Then what happens is that, so remember that we have 4 regimes, not 2. Then if you assume 2 regimes, then you get 2 regimes. Alright? But then sort of, well, so first you are in regime 1, so these are the probabilities of being in any regime. So probability of being in regime 0 first is 1, then becomes 0, and then it goes back to regime 1, regime 0, and then goes to regime 1. Right? So let's look at the top. So probability is 1, I'm in regime 2. Is 0, I'm in regime 1. Right? So you see that? But that is actually not what we had originally. Right? So that's a specified model. And we assume 2 regimes, but indeed we have 4. Right? So what this model does is that it picks the mean. Right? So first is you are in high, then comes in low, then gain goes to high, then comes to low. Doesn't get the variance, because there is a variance shift. But because we fixed it to have just 2 regimes, the more dominant one shows itself. And the more dominant is the mean shift. Alright? But that's a wrong one. Yeah, so that's clearly not correct. But let's increase the number of regimes to 3. Alright. Then somehow things change a little. Alright. So it estimates 3 means and 3 variances naturally. But that's still not the best. Right? So that's not the best model. Alright. So, well, I mean, having say 0, 0, 1, 1 is not a good one, right? And having 0, 0, 1, 1 and 0, 1 may also not be a good one. But we also need 1, 0, another one, right? So 4 models. Alright. It's estimated with 4. Then it actually captures more or less very good the situation. That's, I think I did it somehow. Let's do it again. So now we hit the wrong. Alright, so then we have something which is maybe a little better compared to the previous one, right? So we have 4 regimes, right? And so first you are in regime 1, then you go to regime 0. And why doesn't it actually get it right? The various switching is correct. And so on and so forth. So, well, I mean, here it doesn't get any regime 4. That is what we did the other day. I don't see my problem. So in the last one, okay, but I mean, but the point here is that, so if you want to choose the number of regimes that one you should do, alright, so to say 0, 0, 1, 1, 1, 0, 0, 1, or maybe more, alright, what you should do is, well, that's a question of model choice. Do I have 1 regime, 2 regimes, 3 regimes, 4, or maybe more? And to do that, then what you should do is to look at the AIC. You pick the model that has the smallest AIC. Alright. So here, for example, AIC is 3087 with 2 regimes. And with 3 regimes becomes lower, so that's a better one. And that becomes slightly more, right? So if I increase the number of samples, right, then we will be potentially seeing more of the 4 regimes better. So the sample is too small. Right? But that will take longer. So what I mean is that your question could be answered using the AIC BIC. I'm running not 2 models, 2 regimes, but rather 2, 3, 4, 5, 6, 7, and so on and so forth. And the Markov sort of switching one, will you pick the right model, right? Using AIC. So I basically choose the AIC, then indeed I will be able to sort of get the right sort of model that describes the thing. Right? Yeah? That could also be with the regressions. I could run 2 regimes, and then I didn't do blank. Yeah, I just didn't remember that I had to talk about models of choice here with respect to K when I was teaching. But I could do 2 regimes, I could do 3, I could do 4 and 5 and so on and so forth. And I stay with the one that has the smallest AIC. Alright? And this is still running with a very large sample. So, well, let's see, maybe it will be that's like 10 hours. That's 100,000. That was the problem. So this is well, but that doesn't matter. So that's is 10,000. Right? Well, so that's still with 2 regimes. So I need 3. Oh, so now let's go. Look, and with more observations, and we captured all of the switches. So these regimes do not overlap. and they're separate. So regime 0 is probably the last one. That's here. Right? So that is sort of what we have, because that's where the complete is. Regime 1 is this one, the one which is here. Right? And regime 3 is this. Right? And regime 2 is the first. So that is where the probability is 1. So first we have this, then we have that, then we have this, then we have that. So that's sort of explicitly switches between the regimes. Now let's look at the AIC, just to see the values. Right. So here is 3008, right? That's smaller, 29, and that's 28. So that will be potentially the best model we can get out of the three. Maybe if you had run another one, it will take longer, because the number of parameters to estimate will be many more, so it will be very hard to. We have to stay low so that we can estimate that. And we have to rely on the AIC and model choice. So that was the answer to your question. All right, so time is over in my class and yours too. So we can just turn that off, and thank you very much for being always here and for always thinking and acting and supporting. So that was very nice. I was very happy teaching you the material.
Professor wants to take a picture.
You don't want to do